Yes, I will tell you something about matrices. So, yeah, so maybe I start with, in the spirit of Muhammad's talk, a warning. Okay, so I kind of was enthusiastic about speaking about something, and then the next day I was enthusiastic about speaking about the next thing, and so on. So I kind of cycled through different topics until I arrived at one that I'm not sure has anything homological or mirror symmetric about it. So we'll see. I mean, the motivations are from homological mirror symmetry, but the specific talk is really going to be much more kind of concrete. I don't know. So warning, so only HMS in motivations. Okay, so what I'd like to talk about is joint with Xiaoxian Chen, who's Chicago. And I'd like to start just with an example, a very simple example of the kind of geometry we're interested in. So let's take, let's see if I have notation. Let's just take C2, okay, say with coordinates Z1, Z2. And I want to regard this as a holomorphic symplectic or hyperkähler manifold, okay? So it has two natural, well, maybe many, but at least two natural symplectic structures. So one is the holomorphic symplectic structure, which, okay, maybe I'll take the real part just to, well, okay, let me just write dz1, dz2, and then it has a Kähler symplectic structure, which is, what, dz1, dz1 bar plus dz2, dz2 bar with some maybe I over 2 in front of it. Okay, and let's take the real part of this. Okay. Okay, so these are two beautiful symplectic structures, and I'd like to think about Lagrangians for them. And there's a natural Lagrangian plane. I mean, there are many Lagrangian planes, but let me point out some natural Lagrangian planes for each of them. So for this one, any complex curve is Lagrangian. So examples of Lagrangian planes. So here I could take, for example, inside of C2, I could take, say, Z2 equals 0. Inside of C2. Okay? And for this one, I could take R2, which is just the imaginary part of Z1, and the imaginary part of Z2 equals 0. Okay, and I think it's a, I don't know, easy exercise to see that one can move through planes, moving this two-dimensional real plane to this two-dimensional real plane. And in fact, one can interpolate between the two symplectic forms. There's a family of symplectic forms, and you can transport these Lagrangians as one moves between the symplectic forms. Okay, so the kind of the upshot of this picture that I'm going to try to extract in more kind of general situations is that these two types of Lagrangians are diffeomorphic, in fact isotopic, and through a family of Lagrangians. So isotopic kind of via interpolating Lagrangians. Okay, and that's, for the time being, that's all I want to say about this example. Yeah?
Meaning we simultaneously deform this.
Yeah, that's right. That's right. So I mean, I'm not going to say. So maybe I'll just advertise a question. So to the audience. So I put in the title hyperkähler or some kind of. So everything I'm going to think about, I have no doubt, should be understood as hyperkähler rotation. But I'm not going to be kind of trafficking in that specifically. Okay.
Real and symmetric matrices.
Yes, real and symmetric matrices. Okay. So here's okay. We'll get there.
What do you actually remind you of title?
I'm sorry. Okay, my title okay, is real and symmetric matrices And I'm about to get to matrices. I'm about to get to 2 by 2 matrices. Okay, so these are not yet. Sorry? No, I said in the abstract. Sorry, in the abstract. Sorry. Okay. Okay, so let's now do another example. So let's call this example 1. Let's do a slightly more sophisticated example. Example 2. Let's now take C2 mod Z mod 2, just acting by reflection. And so I will identify this with the nilpotent cone for SL2. Okay, so let me just remind you. So if I think of coordinates Z1 and Z2, then I have, say, coordinates here, let's see, ABC, subject to negative a squared minus bc equals 0. Okay, because I think of elements of this set as 2 by 2 traceless, determinantless matrices. So I have an A, negative A, B, and C. Okay, these are complex numbers. And the trace is 0, and the determinant, the trace and determinant, are both 0. Okay, and I guess just to be, well, okay, and there's a natural covering map from C2. Okay, so let's denote this by N2. Okay, so it's 2 by 2 nilpotent matrices. And there's, there's a well-known symplectic resolution. So this one is a Poisson manifold. There's a well-known symplectic resolution given by T star of P1, mapping to N. If you like, you can think of, let's call this matrix A. You can think of pairs of a line inside the kernel of A, and this data maps just to A. Okay, so that's a symplectic resolution. And now I want to study 2 types of Lagrangians. So one of them this gives you a natural holomorphic symplectic structure. Okay. And then I also have a kind of, maybe I should have said, I have a holomorphic Poisson structure coming from here, and I also have a Poisson structure coming from here. Okay, just by descent. Okay, so, omega holomorphic and omega Kähler descend to Poisson structures. Okay. On this N. Yeah, on this N. Sorry, yeah, I somehow. And now I want to do the analog of looking at certain special Lagrangians. So let me highlight my 2 favorite Lagrangian subvarieties. Okay. So let me do the real case first. So we'll have the kind of holomorphic and real. So the holomorphic and the real. Okay, so the real one is easy to say. I just take this quadric and I take its real points. Okay, so I can look at N2 of R inside of N2. Okay, and that's a real quadric, which is literally this picture. Okay. On the other hand, I have a favorite holomorphic Lagrangian, which is given by, if I look at the points as matrices, I can look at symmetric matrices. Okay? So I can look at, let me call it N2 symmetric, okay? Which will just be those matrices A, so that A equals A transpose, okay? Which just means that I have A and B, and they satisfy what negative A squared minus B squared equals 0. Okay. Okay, sorry, the board management is not very good, but this, of course, just factors into 2 linear equations, so I can draw it as just 2 lines in the plane, in the AB plane. Okay, so this is an R picture, and this is kind of an honest topologist picture, and this is a C picture. Okay. So, so this is really 2-dimensional, but I can't draw it. Okay, and the exercise for you to do, if you want to tune out the rest of the talk and just do some fun exercise, is to do what we did here for these two Lagrangians. Okay? So one can rotate, for example, this picture into this picture. Okay? So find an isotopy between these two Lagrangians. Okay? If you like, find the interpolating symplectic forms.
Sorry, in where?
In this Poisson manifold. I mean Poisson variety. So I have a two-dimensional Poisson manifold. It's just C2 mod Z mod 2.
It sounds like
I'll solve the exercise.
there's a risky tangent spaces and the singularity, like reals of risky tangent spaces of different dimensions.
Absolutely. So that's
By isotopy.
I mean, I'm a topologist. I don't know. We're a topologist. So I just want to move these subsets via some, okay, isotopy, maybe
It's not dichotomy.
homotopy. Yeah, homotopy. I don't know, homotopy. I mean, all right, let's find a homeomorphism. Okay, find a homeomorphism. I claim you'll be able to do it in a parametrized way. In fact, so find a homeomorphism between these two, and you can do slightly better. Each of these spaces has a natural symmetry group, which is just given by the orthogonal group acting by rotations and reflections. So the exercise is to find a homeomorphism that's O2 of R equivariant. Okay, we'll solve the exercise together in a moment, but I just wanted to. Does that make sense? Okay, so here we solved it. I mean, maybe we didn't solve it, but it's obvious, I think. And so the solution to this exercise, okay, a solution is to just look at the preimages inside of here. Okay, so I started this by telling you that this was C2 mod Z mod 2, and you can just look at the preimages. Okay, so we can look at C2 mapping to C2 mod Z mod 2, which is our N2. Okay, and if you look at the preimage of each of these, what you will find, for example, the preimage of the real locus is going to be this copy of R2 together with its imaginary rotation. Okay? So the kind of preimages, so we have the real and the holomorphic. So the real preimage is R2 union IR2. Okay? And the preimage of the complex will be two coordinates. Okay, I'm not sure I parameterized it correctly, but I hope it's also, so it's C union C. Okay? Okay, and now you just repeat what we did before, just with these, keeping the crosses, so to speak. Okay? Now, as Paul pointed out, something very strange is happening when one passes to the quotient, in that this copy of C is mapping to this copy of C. This copy of C is mapping here. But this copy of R2 is, for example, only mapping to one of these components. Okay, so there's a kind of funny business going on with these maps that's changing the kind of algebraic dimension of these. Okay, so a goal of the talk is to generalize this, to explain a generalization that I think is I don't know how to say it. So every theorem I think I've ever proved has been homological, and this will be, this will not be a homological statement, but then if there's time, I'll explain some kind of homological motivations. Okay? So, yeah. Okay, great.
Families of algebraic structures on this. If you think that it's a hypercalic thing, it's actually a family complex structure.
Yeah, okay.
And don't we expect that as you move that family of complex structures, in fact, changing?
Okay, so what I think is happening here is that this, we have good intuition for smooth things, but at the singular point, something funny is happening.
R2, IR2, are those complex are actually complex lines for some hypercalar rotated structure?
Probably, yes.
So then that makes your isotopy kind of very much more reasonable.
Great. Okay. So okay. I mean, I'm going to try to explain to you some moduli spaces that make it reasonable, but they won't have the words hyperkähler in them. So that's kind of sorry.
But can I put them in?
That's what I would love. Okay. So every time I've ever talked about this, the audience has always said, "Aren't you just doing a hyperkähler rotation?" And the point is yes, but I don't know somehow.
But there is a really puzzling aspect of this, which is, so is this picture lifting to the resolution or not?
No. So this is why I said if you analyze what's going on in the resolution, so as you move, for example, like these guys lift to some real form of the resolution, okay? And what happens is they get kind of ripped into a kind of singular, let me draw a picture, I don't know. So, maybe I cut you off. Did you want to say more, or can I just draw?
No, I just want to say that there are two hyperkähler structures on the tangent of P1, which behave very differently. So if you have an interpolation between these two things, in one of them, what is happening in the other one?
Okay, so I'm going to draw the picture, and then, okay, so let's draw a picture of this kind of resolution and what's going on. Okay, so now I'll just draw this kind of complex picture. So here's N2, and then upstairs we have this resolution. Okay, so this is T star P1. Okay, now I don't, I can use colors, great. Okay, so it's kind of hard to have enough dimensions here, but like this, maybe what I'll do is I'll draw fronts so you can see what's happening with the fronts rather than, okay, so this T star P1 is of course the cotangent bundle to P1. Okay, so here's P1. Okay, and now I'm going to draw for you what you see is the preimage, for example, of this, the kind of proper transform of this, okay? So if you take this real cone and you look at its preimage, okay, what you will see is the entire zero section together with the conormal to the real RP1. Okay? So let me throw out the zero section. Let's just look at its kind of proper transform. Okay, so you see this green. On the other hand, if you look at these two lines and you take their preimage, again you will see the whole zero section, but you'll also see conormals to these 2 points, say 0 and infinity. Okay, I and negative I. Okay, so I and negative I, and this one is RP1. Okay, now what's happening, if you just follow through the most obvious thing to do, what's happening is you take this green, I'll just draw an intermediate step in the movie, okay, and start to, there's not going to be any chuck left, start to expand it to a band. Okay, so start to expand the green to a band, okay? And you have in mind that you're taking the zero section maybe together with the outward conormals to the boundary. Okay, so I started with both kind of conormal directions, and then I just start to expand the band, and then the band collapses, and I get the conormals to these 2 points. Okay? So, okay, that's what's happening in the resolution, and I think the key point is that this band is not part of that story. So somehow what's happening away from the zero section is a nice isotopy, but this kind of band is not, okay. I don't know if this is relevant to your comment, but okay, it's a picture. Okay, so now I'd like to state a theorem that's going to guide kind of what I discuss. So the theorem is just going to be the generalization of this to higher rank. Okay? So, theorem, it's in a preprint on the archive from, I don't know, last fall. Okay, so now I will look at nilpotent matrices, so n by n nilpotent complex matrices. Okay, so that's the ambient Poisson manifold. And inside of it, I can look at two natural subsets. It's real points, okay, or those complex matrices that are actually symmetric. Okay? So these are cut out by A equals A bar, and these are cut out by A equals A transpose. Yeah.
Yeah, but those are isotropic for different Poisson structures.
Yeah, I mean, that's right. So this one lives in the world of like the symplectic resolution and holomorphic symplectic geometry. This one is kind of very natural from that point of view. And this one is a kind of Kähler object. Okay, they're cut out by these, plus of course, nilpotent means the characteristic polynomial is 0. Okay. Okay, so that's the setup, and now what's the statement? Maybe I try to put it here. I'll put it up here. It's got enough words. Okay, so the theorem is that there's a homeomorphism. And again, we can strengthen it in various ways with the appropriate language between these two. And it's O and R equivariant. Okay. No, okay, so what, I knew, so I sort of opted to talk about GLN because this is not a Lie theory conference, but no, I mean, so we understood something about classical groups because they kind of come from GLN by some structural reasons. You'll know very well as I kind of explain how we prove this, why exceptional groups are still kind of a little bit beyond what we understood. All symmetric. I mean, okay, so there's a theorem about all real forms and so on in symmetric spaces. But say all classical real forms in symmetric spaces. Okay, we didn't understand exceptional groups. Okay, so if you're interested in E8, I mean, what I will tell you. So let me say when I give some arguments, I'm going to prove. I mean, this is kind of a piece of what I think is a more natural theorem about Grassmannians. So. Okay, yeah. So let me. Okay, let me finish the statement, and then. Okay, so the one thing to say is that the way we will prove this is not just by, of course, writing down a set map, but by finding some interpolating family of spaces. So a more remarkable statement I found is the statement that there exists, in fact, a family of involutions interpolating between conjugation and transpose. Just geometric involutions on the nilpotent cone.
But not on matrices.
Not on all matrices. There's a generalization to matrices with real eigenvalues and so on, but I won't. Yeah. So there are various generalizations as you deform the symplectic, whatever resolution. But okay. So this, to me, was a kind of, I don't know. I've thought about real groups for a long time. It's kind of a surprise that there would be such a structure. Okay, so let me now, Sasha said something about a homological mirror symmetry. So let me mention kind of what's been, this is not out of the blue. There's various results about this before that kind of inform this, but then I want to also mention where I'd like to take it. Okay, and then the rest of the talk will be somehow about the arguments that go into it. Okay, so just some remarks. Okay, so first remark is that there's a well-known theorem about the orbits on these, the set of orbits. Okay, so there's a theorem called the Costant-Iguchi correspondence, okay, which I've been told one should not attribute it to Costant. I don't know. This is maybe a point of some debate at some point. But anyway, due to Costant-Iguchi, and then also Cronheimer and Michel Verne okay? Which tells you that if you took the real matrices and say divided out by GLNR, acting by conjugation, that this set of orbits, okay, so poset of orbits, is isomorphic to the poset of orbits on the other side that you would naturally write down. So you take orthogonal complex matrices. Okay, so the kind of possible Jordan forms, so to speak, of these matrices are known to be in bijection. Okay, and moreover, the orbits, I don't know, O real matching with O symmetric, are known to be, diffeomorphisms. Okay. So the kind of new piece of information here from the perspective of these old results is in fact that the way these orbits are put together is the same on both sides.
Is that known for other groups?
Yeah, this is known for other groups, not even classical, all groups. Yeah, okay. So I thought if I gave a talk in which I started with G's and K's, I would just lose everyone, so I... Sorry?
You would have gotten booed.
I would have gotten booed. Okay, so I decided just on GLN and, where most of the content is anyway. So, okay. Okay, but all right, so this is not a homological remark, but now let me make a homological remark to answer the question. So Sasha's question about isn't there some homological, okay, so second remark is there's a beautiful story. If we look at branes on here, okay, so let's say we study branes on here for one of these two different symplectic structures supported on these Lagrangians, okay, then those two categories of branes are known to be the same. Okay, so that's an informal statement, but it's what's called Matsuki duality. And this is due to Matsuki and Mirkovich, Uzawa, and Vilonen. And again, just to paraphrase, if you look at, this will be in quotes, A branes on N supported on the real points, okay, are isomorphic to A branes on N supported on the symmetric points. Again, that's why I put it in quotes. Go to the resolution, pick your favorite tool that quantizes the resolution. Fukaya category, sheaves, D modules, whatever you like. Go to the resolution and then look at those branes that are supported on the kind of proper transforms of these, or pre-images of these, and you'll have this equivalence. Okay, so for this equivalence, you don't need to know such a kind of strong statement that these are homeomorphic. But so the last comment I'd like to make, and maybe I'll get to it by the end, is kind of my motivation and why I want this kind of stronger statement and where it came out of, is I want to treat, for example, this as a symplectic manifold. Okay? Poisson manifold, and study the branes in it. Okay? So I want to, let me say it in a kind of more precise statement, so motivation, so study A branes in, again, this will be in quotes, in T star N N R T star N N sim.
Why is that a different thing from what's...
Okay, so here the symplectic manifolds are just different symplectic manifolds. Okay, so what's up here is like, okay, let me say things in terms of sheaves, just for precision, since Vivek asked. Okay, so in this situation, what you end up studying is sheaves on a flag variety with certain singular support conditions. Okay, what I want to study is sheaves on, say, real flag varieties with certain singular support conditions. Okay, so I'm not studying sheaves on the complex varieties. I'm studying sheaves on the. or on this kind of not orthogonal, kind of symmetric flag variety. Yeah. Okay. And the motivation is this has to do with representation theory of things like GLNR. Okay, so I don't want to go into this, but the point is that there is a homological motivation for this, but you need something stronger to kind of prove some results, like I want to do real Springer theory and other kind of constructions, so you need this stronger result. Okay, so I fear that I'm losing, outside of Sasha, lose the audience. So I'm done with motivations, and I'd like to just focus now, okay, if you'll kind of join me, I'd like to just focus on the geometry of this statement. Forget all homological mirror symmetry or branes and so on. I just want to explain to you how to construct a family of involutions interpolating between conjugation and transpose. Kind of a, I don't know, kind of surprising structure to me. Okay? Okay. So, so done with motivations. Okay, so let me talk about the proof of the theorem, and let me say we're really a kind of better theorem. I don't know. Okay, so I'm going to prove. I'm going to give a theorem, give a proof that proves something of this form, of which this is a piece of the more kind of bigger thing. Okay. So I'd like to just remind you of a way to rethink about nilpotent matrices. Okay, so if we look at nilpotent matrices, we can just just take their spectrum, and we get an isomorphism with torsion sheaves of length n on, say, A1, or I'll even put P1 just for future, that are supported at 0 and are, say, framed. Okay? So a nilpotent matrix is the same thing as a torsion sheaf supported at 0 on A1, so in particular on P1, and I have a basis because, of course, the matrix came from a choice of basis. Okay? Okay, and so the correspondence is A goes to T minus A. C of, if my parameter here is t, goes to C of t, t minus a. Okay. Okay, so that's the first trade-off. Okay. And so what I like about this picture is this P1 is now playing the role of eigenvalues. So this is like the eigenline. Okay. And now I'm going to play games with eigenvalues. Okay, I'm going to move the matrices around by moving the eigenvalues around in P1. Okay? Okay, now the second step I'm going to take is the following. So I'm going to, sorry, this is not going to be an equivalence, this is going to be an embedding. Okay? I'm going to embed these things in the affine Grassmannian for GLN. Okay? So let me just remind you what the affine Grassmannian, if you like, is I take n by n matrices where I look at Laurent polynomial entries, so say T inverse, so C T inverse. Okay? And then I divide out by, sorry, I'll do it like this. I divide out by polynomials in T. Okay, so this is a beautiful infinite dimensional Grassmannian. The reason it's called a Grassmannian is one can write these as lattices in an infinite dimensional vector space. So let me just remind you of that picture. Okay, so this is just kind of continuing. So this picture you can describe as the following. It's isomorphic to lattices. So I look inside of, say, C T inverse. I look at complex subspaces, say W, okay? And these are C of T lattices, so they're modules of full rank, okay? And that's this moduli, okay? So you can think that this is the Grassmannian of this vector space for subspaces that are close to the holomorphic maps, Okay, and the map from, say, the original matrix A to the Grassmannian, one map you can give is just, you can send it to, say, 1 minus T inverse A. Okay, so this is a map, G of T, is given by 1 minus T inverse A, and this embeds your nilpotent cone inside the affine Grassmannian. Okay. Okay. Now, okay, so now what I'd like to do is forget the nilpotent cone. Okay? So the affine Grassmannian is like the nilpotent cone. It has a beautiful holomorphic symplectic stratification, and so I'd just like to study the affine Grassmannian and forevermore forget the nilpotent cone. Okay, so with your blessing, we will now never deal with nilpotent matrices again, but we're just going to study this kind of affine Grassmannian. Okay?
Before you leave nilpotent cone.
Yeah.
So the isotopy that you have at matrix up on the resolution is going to be conic?
The isotopy. No. So when I start to do it, you'll see what happens. Well, okay, yeah, no until further discussion. Okay, so from here on, so let's focus now on this affine Grassmannian. Okay, and in particular, I'm going to focus on a very nice subset that, you know, the nilpotent cone was affine. This Grassmannian is not affine, but it contains inside of it a nice open affine subset. Okay? So I'm going to focus in particular on an open this kind of open subset represented by maps that only depend on T inverse. Okay? Or equivalently by lattices that are transverse to the opposite lattice in T inverse. Okay? So this is, so the lattices are in C of, oh sorry, there's an N. Yeah, thanks, okay, yeah. So the lattices are in here, and I can look at, so this subspace is going to be G independent, G of T inverses, things represented by G of T inverse, so independent of T, okay? And that's the same thing if you follow this through as lattices W that are transverse to C of T inverse to the N. Okay, so it's an open subspace. It's like an open Schubert cell inside the Grassmannian. Okay? Okay, so you know, before we were studying the nilpotent cone, and now I'm going to replace it and just study this one. Okay? And this one has the kind of same beautiful formal theory that the nilpotent cone has from a symplectic point of view. Okay, so let me remind you now of the beautiful behavior of this Grassmannian as one varies eigenvalues. Okay, so right now I'm studying everything is based at 0. Like I introduced P1, but I never left a neighborhood of 0. But we're about to leave a neighborhood of 0. Okay, so I want to just remind you of some beautiful factorization properties of the Grassmannian. Okay, so the Grassmannian has yet another interpretation, okay, that I'll write down specific to this setup with P1. Okay, so it is the same thing as I look at a rank n vector bundle. Okay, so E to P1, so rank n vector bundle on P1, okay, together with a trivialization away from 0. Okay, so tau from E naught, let me write it here, whoop, oops. Okay. So tau from E naught to E restricted to P1 minus 0 is a given trivialization. Okay? And the way you see the equivalence is probably most easy to see here. This is the gluing data for a G bundle, a GLN bundle on P1, a vector bundle. And I divide out by gauge on one piece, but because I keep this trivialization on the other, I don't divide out by gauge. Okay? So the Grassmannian is simply this moduli of vector bundles with a trivialization away from 0. Okay? And now, let me remind you of the beautiful factorization. Okay? So now I can start to look at this moduli where I allow trivializations not necessarily just away from 0, but away from finitely many points. Okay? So I can look inside of P1, okay, and I can allow some collection of points to travel around. So I have in mind that they're eigenvalues. Well, okay, anyway, let's write A1, A2, all the way up to some AK. Okay? And now I can repeat this definition. So I can look at the Grassmannian n P1 with k points. Okay? So this consists of these points, A1 through AK, inside P1, okay, together with the data of a vector bundle, and now also a trivialization away from these points. Okay? So tau is a trivialization of E away from the points A. But let me just write A for the kind of collection of these points. Yeah? Right, so the one way to interpret going from here to here is I'm resolving all my torsion sheaves. And I mean, I'm just repeating your question. So now don't know if I'm going to answer your question, except that this factorization is what I want. And I probably could rewrite it all in terms of torsion sheaves, but it's for me anyway, it's easier to understand in terms of free sheaves, locally free sheaves. Yeah, so the correspondence between like here and here is if you have a torsion sheaf, I will resolve it essentially by this map between free sheaves, locally free sheaves. I think it's what you said. So if this W will be the kernel of a surjection from a free sheaf to the torsion sheaf. Okay, up to maybe twisting by some, a point. Okay, and now the beautiful statement is that this factorizes. So this Grassmannian, its fiber at some point A is equal to a product of these original Grassmannians, or is isomorphic to a product of these Grassmannians, and the number of them is just given by the size of the subset A. Okay? So as you allow your eigenvalues to spread out, your notion of matrices now spreads out and kind of collides together in interesting ways. Okay. Okay. So okay. So now I think I'm ready to kind of give you the proof of the theorem. So let me state a kind of a theorem about this Grassmannian that will imply the one about the nilpotent cone. Okay, so this is what I said, a better theorem. I don't know. Okay, so we look at inside of the Grassmannian, and we look at this open locus that I specified. Okay, so inside of here we have two subsets. One is the real subset. So just the real points. So everywhere here where I said lattices and so on, you just put the real numbers instead of the complex numbers. Okay. And then I also have what you could call the symmetric subset. So Grassmannian 0n symmetric. Okay. So these are represented by n matrices and Laurent polynomials that are real. And these are represented by n Laurent matrices that are symmetric. Okay. Yeah. All right. So let me continue, and then you'll see exactly what it means. Okay. So okay, and we're going to prove that these two things are isotopic or homeomorphic in a kind of respecting all symmetries. Okay? Okay, so we're getting late in the talk, so let me draw a picture. I won't give you the proof, but I'm going to draw a picture of the proof. And then talk about the picture for a few minutes. Okay, so the picture of the proof is the following. So we start with P1. Okay, so here's P1. And I can't remember which way I draw it. Here's the real locus. Okay, so here's RP1 inside. So RP1 inside of P1. And here's, say, the point 0. Okay? So this moduli, okay, is concentrated at this point 0. Okay? It consists of, again, if you like, matrices in T inverse that have real coefficients. Okay? So what I'm going to do is take 0 and split it up into 2 conjugate points. So there's going to be a family where I take this point 0. So here's 0 is in yellow. And I'm going to split it into 2 points A and A bar. Okay? So this will kind of degenerate back. Okay? And then I'm going to do the only other degeneration available is I'm going to degenerate the curve P1 itself. Okay, so I'm going to look at this moduli where now A is here and A bar is here. Okay? And during this whole family, I'm going to keep track of the Galois structure. So RP1 was the real points of a Galois structure. And it continues to be the real points of a Galois structure. Okay? But remarkably, when you go here, there's only one real point. So what's going to happen is all of the gauge theory is going to decouple from the Galois structure because the Galois structure is going to be concentrated at a single point. Okay? So let me now, okay, so that's the picture. If I will now continue for the next few minutes, but I think this is the main thing to see. So I'm going to somehow take nilpotent matrices, spread them out to kind of conjugate things, and then degenerate the possible eigenvalues themselves. Oh, the Galois symmetry like this? Is that? Yeah, so the right-hand side is going to involve symmetric matrices. So this is going to be the answer to Sasha's question is, what do I mean by this? So one interpretation will be certain matrices that you see here. That's right. So this is going to be the kind of real picture. This is going to be the symmetric picture. That's right. That's right. So what's happening here is the Galois symmetry reflects these two, and so the moduli spaces essentially don't see the Galois symmetry because this is more or less a free action. So because it's a free action, you don't see any kind of real structure except from what comes from this point. Okay. Now, so you can ask what's going on in the middle, and this is kind of relevant to Vivek's question. I think he's fallen asleep. They're relevant to his question before about dilation variance. So what goes in the middle was or is my original motivation. Okay? So what goes in the middle, I won't tell you about these moduli spaces that I'm going to associate, but what goes in the middle are period domains for loop groups for L, G, R. Okay? So this is the object that I'm interested in. Okay, I know very little about it, but I do know that it has topological degenerations to these two moduli that are kind of iso-trivial. Okay, so I'm really interested in this, and this whole story is telling you that I can study it via these guys. Okay, so that's kind of where we're headed. Okay, so let me say a word or two then, just in the last few minutes, about the moduli spaces associated to this picture, the gauge theory on this picture, and why it gives you this kind of a story. Okay? I don't know, have I lost it? It's okay? Okay. So, okay, so let's first let's start just with Grassmannians and then add to it Galois structure and so on. Okay, so let's just start with complex Grassmannians on each of these pictures as I defined there. Okay, so let's pass to Grassmannians. Okay, so what do we see on the left-hand picture? This was our original Grassmannian. Okay, this is just the Grassmannian of vector bundles trivialized away from 0. Okay, so if I draw fibers of some, I'm going to draw fibers of some family of moduli just like I drew fibers of some family of curves. Okay, so on the left-hand side, I'll just see Grassmannian of n. Okay, now the 2 points separate, and by this factorization, I see in the middle 2 copies of the Grassmannian of n. Yeah.
So 2 points separate. So this point here, 0, has some kind of multiplicity to start with?
Okay, so all of these moduli are kind of, maybe this is one reason to like this, it's all erased, this formulation, oh no, here it is, this formulation better than torsion sheaves. All of my data is on the complement of this point. So you'd actually have already kind of removed a, formal thing, if you like. Okay? So the moduli, when I say pass to Grassmannians, what I really mean is pass to this definition. Okay? So you're studying vector bundles together with trivializations. If the trivialization is ill-defined at these 2 points, we have the remarkable factorization. Balance and Drinfeld gives us this factorization that tells us we get 2 copies of the Grassmannian rather than something kind of more complicated. And when they collide, we get 1 copy of the Grassmannian. Okay? So it's remarkable. There's a family in which the generic fiber is bigger than the special fiber. That's kind of, I don't know, very strange, okay, but true. Okay? Now, what happens when we go down to this side? Well, we still get 2 copies of the Grassmannian. I mean, the kind of trivializations trivializations exist all the way from these points, so I can cut out everything and just sew in a genus 78 curve. It doesn't matter, okay? So what I see here is just 2 copies of the Grassmannian. Okay? So that's just what we see by invoking this definition for this family of curves. Okay? Okay, now I'm going to divide this family by some natural symmetries. Okay? So I'm going to quotient by unitary symmetries. Okay? So let me explain what I mean by that. So now I'm going to introduce the Galois action back into the picture. Okay? And I'm going to look at maps from P1 minus the eigenvalue points, okay, into GLN. And I'm going to insist that when you flip by the Galois action, you flip by the conjugate transpose inverse. Okay? So inside of, so maps, I can always look at maps from P1 minus whatever marked points I have to GLN. Okay? And inside of this, I have this group scheme called those maps that are unitary for this real structure. Okay? So I have a kind of, I don't know what notation to use, U sub A. Okay? So these are unitary maps. Okay? So let me just tell you what this family, this group scheme looks like as one moves. Okay? So, so on the left-hand side, you can ask, what maps can I map from A1 to GLN so that, in particular, the real line gets mapped to unitary matrices? And the answer is they have to be constant. Okay? So the fiber on the left-hand side is just UN. Okay? Now the 2 points split, and you can ask, what maps can I map into UN from P1 minus these 2 points? And the answer is a whole loop group of maps. Okay? So what you see in the middle is LUN. Okay? And then it degenerates. And now I have to write down any map here. And all the unitarity structure says is the map here and the map here must be conjugate. So the only place it needs to be unitary is at this point. Okay? So what I see then is the map, the group, say, G of T inverse, GLN of T inverse, but now infinity needs to go to UN. Okay? So I have this family of group schemes, this group scheme over this family of curves. The generic fiber is the loop, the unitary loop group. The special fiber here is just constant, and here it's some other beast. Okay? And I told you what I'm going to do is quotient by these unitary guys. Okay? So let's do it. So what one sees, so the quotient, so this is the quotient. So I'm quotienting, star by double star. Okay? So on the left-hand side, I just see a copy of the Grassmannian mod the unitary group. That's a finite dimensional group. And now in the middle, I have the remarkable property that the unitary loop group acts transitively on the Grassmannian with stabilizer this group. Okay? And so what I see here in the middle is also the Grassmannian modulo the unitary group, and this degeneration is topologically trivial. Okay? Now on the right-hand side, what I see is somewhat mysterious, but inside of it there's an open locus that just looks like what we were calling Grassmannian N0 modulo the unitary group. Okay, so this is open. Okay, so I don't want to try to tell you what the quotient of this is by this. I'll just tell you that there's an open subset that looks like this. Okay, and this is again trivial on the open part. Okay. Okay, so I'm running out of time, but I just want to point out that so what's happened here now is we've arrived. So somehow the rest is just going to be playing with involutions. We've constructed in an incredibly complicated way a trivial topological family. Okay, this is a family this is open in this, so it's a kind of essentially topologically trivial family of spaces. Okay, but the presentation in terms of their moduli is very different at the different ends. Okay. And now if you now impose that you really want real matrices throughout this family, what you will find is that inside of here you will see Grassmannian N R mod ONR. Okay, so this is kind of Galois fixed. Okay? And what you will see here, you will feel happy defining as symmetric matrices. In particular, it has like the symmetric nilpotent cone naturally sits inside of it. Okay? So what you will see here is Grassmannian N0 symmetric mod ONR. Okay? So my point is that at this stage, once you have this kind of trivial family, but set in this kind of moduli theoretic way, passing to these kind of Lagrangian subspaces gives you these two different Lagrangians. So I started the talk by saying, we have these holomorphic symplectic things, and they have two different Lagrangians in them. And now, in fact, I've made a family of these holomorphic symplectic things for which these Lagrangians just kind of travel through the family. Okay? Now, the question to the audience, and then I'll finish, is explain, is this a hyperkähler rotation? Okay? No. Okay, so Paul says no. Do you want to comment? Or okay. Maybe. Okay, maybe I just say one more thing, which is that the thing again that really interests me is what goes here in the middle. There is a space that goes here in the middle that has an interpretation in terms of period domains, and I'm interested in the kind of homological mirror symmetry for those things. Okay, thanks very much.
Thank you.
So Vivek asked, is there a dilation? Is there a natural dilation? Is everything? And the answer is really no. Like this picture has a clear like GM action on it. Well, this one has a GM action, okay, and this one has GM actions. Just kind of if you fix A and A bar. But the point is, there's no GM action on the entire family. As I collide these points, like this degeneration doesn't respect the GM action. Okay, so that's why I said I hesitated to say it's not dilation invariant unless you kind of, I don't know, by hand put it in.
But it seems like the naive thing is that the total family has some kind of.
Yeah, that's right. So the total family has actually, it's kind of over P1.
Yeah.
It's a total family over P1 with a kind of limit at this end and a limit at this end. That's right. But what's here in the middle kind of moves A and A bar and moves the curve and yeah. So, well.
But it gives you some group scheme that's disconnected at infinity. It has two C stars.
That's right. That's right. I mean, we well know that C star can kind of degenerate to 2 C stars. And here it's C star degenerating to A1, which also, happens. So. Yes.
Correctly, that this time correspondence story is general.
That's right. That's right.
So, and then there was not general the relation with golden poles. In particular, means that if the time correspondence story is general, then you probably get a bunch of single statements, but just not for the golden pole, but for this kind of
that's right.
And the time correspondence.
That's right.
Right, but you also need an involution to start with, right? I mean, you basically need a real group.
That's right.
So do you get some series of statements for any real group?
That's right. So this theorem is completely general. I mean, I wrote in the sense that you could take n away and put g here, and any real form.
And sim means some evolution.
Yeah, sim means some holomorphic version of some Galois structure, real Galois structure. That's right. So this theorem, that's why I said this is kind of the better theorem. This is the completely group theoretic theorem. Yeah.
In the semi-evolution, or it means the Cartan evolution?
No, so here, to define this, I just need a real form of G. Now,
It doesn't have to be split.
No, it doesn't have to be split. I mean, the more split it is, the more interesting it is. So if things are compact, I will eventually tell you, like, the compact groups don't have nilpotent cones. So I will eventually tell you, like, a point is homeomorphic to a point. So, I mean, the GLN story is in some sense like the most interesting. I mean, it's kind of maximally split. But there's no restriction on type.
But in the GLN case, we get some interesting things. For example, other slices, like for you get some potentially, you have all 2 varieties of type A inside.
Yes. Yeah. So I believe our constructions are kind of, what do you say, kind of completely functorial in vector spaces and vector bundles. So so I think you can. Yeah, the geometry of these is rigid enough that if you write down a homeomorphism, you must respect the G of O orbits. I mean, they kind of, the singularities change enough. So I didn't say that, but all of my homeomorphisms turn out to be stratified homeomorphisms.
And is the superscript 0 important?
So it's important, oh yeah.
I mean, 0 is also saying that the vector bundle is globally trivial.
Yeah. Yeah, I mean, in fact, you can remove the 0 at the price of when you go to this end. You understand, let me say broadly, there's some kind of natural monad here. All right, let me say just kind of a good comment that this should be thought of as this side of the picture should be thought of as a Windberg degeneration for the loop group. Okay, so what you're doing is a Windberg degeneration for the loop group, and you well know that that's not like an equivalence, I mean, that kind of horocycle transform, but you can understand how to recover things from that. So this degeneration is just always an equivalence, but this one is kind of a, so I kind of restricted it to an open Schubert cell to kind of extract something, but you can extract much more.
More questions? Let's take David again.
Okay, thanks.
And the next talk is in 8 minutes.
Oh, sorry.